All right, we've looked at solutions to systems of DEs, and we've seen the relationship between eigenvectors and eigenvalues, and we're going to do more of that, but we're going to focus more on just this idea of stability and the general behavior. So we're still looking at systems of ODEs. In particular, we're looking at linear systems. And the question we want to address now is, what's the general behavior of these solutions? Do they grow? Do they decay? Do they oscillate? Okay, so what's going on is we're assuming we have a linear system, in this case of ODEs. So we're assuming we can write them in the form, the derivative of a state vector is a matrix times a state vector. And what does that mean? So we're assuming our state vector is a column vector, so it has n rows in one column. And we're assuming the matrix is a square matrix, so it has n rows and n columns. And what does this mean? This means that x of t is a function of time. So it has these n solutions, and it's in an n-dimensional space, and basically you can think of this as a path in whatever dimensions we're working in. Okay, and this is exactly like what you saw in your Calc 3 class when you were looking at parameterization of paths. So now the question is how did we solve this? Well, what did we do? So the question is how did we solve differential equations in this form? And we did it in a couple steps. First, we determined the eigenvalues. So we're looking for values of lambda that make the determinant of a minus lambda I equal to 0. Okay. For each value of lambda, we determine eigenvectors. Maybe be careful here. These are some v's, where AV equals lambda IV. And we saw there are situations where we could get multiple v's for the same lambda or just a single v. And that is extremely important because we said if we can find n independent vectors v that satisfy this equation, then we can get a solution in the form of C1 e to lambda 1t v1 plus C2 e to lambda 2t v2, and continue that all the way out to the last eigenvector. Okay, and I should be careful. We called these lambdas, these lambdas are eigenvalues, and these v's, we called them eigenvectors. Okay, and in this case, C1, C2 to Cn are constants. Okay. So let's step back a second and look at this. We've talked about this before, but what did we find? We found that if we can write, this is a big if, our solution in this form, and note there's times we cannot do this. So each of these v's are constants, they're constant vectors. These c's are constant scalar values. The things that are changing in time are these exponential terms. And what could happen with these exponential terms? So let me be careful. Let me call this lambda j. And these lambdas we can write as complex numbers. And sometimes they're have imaginary parts, and sometimes the imaginary parts are zero. And we've seen both of those situations. But we know that when we look at e to the lambda times t, if we can write it as a complex number, then we can multiply that t through, and then we can write it as multiplying these two things. So in this case, so A and B are real. So, and because of that, we can interpret this, and we can interpret this separately. So here, if this is negative, we get exponential decay. If it's positive, we get exponential growth. And for this term, we get oscillations, right? Because this is, we can just use now that Euler's formula. We can write that as sines and cosines. Okay. So that means that, coming back to this expression, just looking at that alone tells us what we need about the general behavior of these solutions. So we're assuming we can write our x in this form. Oops, that's 1, 2, v2. And we're assuming we have n of these things, which means then we can take a look at each of these eigenvalues. Each one we're assuming, this should be A, B, I, B2, I. Each one we're assuming we can write as complex valued. And note if they're real valued, then that means that the B value is 0. Okay. So what does it mean to be stable? What it means to be stable is that we don't see growth. In fact, we see every term decay. And that can only decay if every A value, if the real part of every eigenvalue is 0. So we need the real part of every eigenvalue to be negative. So that has to be true for all of those i's. That means I goes from 1, 2, 3 on down. To be unstable, I just need any one of these things to grow out of control. If any one of these things gets big and I add it to other things, it's going to dominate. So we really need only one, or any one satisfies that the A is positive. So that just happens once. And then we're going to grow exponentially. And it's going to grow in whatever direction we specify. Okay. For oscillations, we just need one of these. So if B sub I is not 0, then we're going to get oscillations. Okay, and that means we're going to get sine of bt and cosine of bt in our solutions, which means that b times the period is 2 pi. Okay, and we can figure out the period of oscillations from this relationship. Okay. So let's look at a special case. And in this special case, we're going to look at a 2x2 system and ask, what does this mean? So if we have a 2x2 system, we're assuming our matrix A can be written in this form. So this is the matrix A we saw before, and it's a 2x2 matrix. So it has entries A, B, C, and D. And this means we can have 0, 1, or 2 eigenvalues. Okay. Okay. And if we have less than 2 non-zero eigenvectors, the method we've discussed so far for getting a solution fails. Let's stop and focus on the case where we have 2 non-zero eigenvectors. And let's just ask what happens in this special case. Okay, so the idea then is then we have lambda 1 and v1, where a v1 is lambda 1 v1, and we have lambda 2 v2, where a v2 is lambda 2 v2, and v1 and v2 I cannot write in terms of one in terms of the other. So that means that our solution is going to look like c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. And what we've seen so far is that if they're complex valued, they're going to be complex conjugates of one another. But the question is, what could happen? Okay. So what do we have? We have a differential equation in this form. A is 2 by 2, and we're assuming we have 2 independent eigenvectors, which implies my solution looks like c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. Right. And we're going to have basically 3 cases. Okay. For case 1, we're going to have that the real part of lambda 1 is greater than 0, or the real part of lambda 2 is greater than 0. And let's just assume that the imaginary part of lambda 1 is the same as the imaginary part of lambda 2 is 0. So another way to say this is lambda 1 and lambda 2 are real, and be careful, at least one is positive. If that happens, that means at least one of these things is going to grow, and it's going to be unstable, and it's going to grow like e to the lambda it, where lambda I is bigger than the other lambda. So this is the largest lambda. Case 2 is that they're real valued. So that means the imaginary part of lambda 1 and the imaginary part of lambda 2 are both 0. And the real part of lambda 1 is less than 0 and lambda 2 is less than 0. If that's the case, this is going to decay to 0, this is going to decay to 0, and we have this thing is stable. Okay, case 3 is that we have complex valued eigenvalues. And this means that lambda 1 is going to be A plus BI, and lambda 2 is going to be A minus BI, where B is not 0. Okay, and if this is only true if A has real valued entries in it, in that case I have to have complex conjugates for my lambda 1 and lambda 2. And now my x is going to be C1 e to the A plus BIT V1 plus C2 e to the A minus BIT V2. And we just saw we can write this as e to the AT e to the BIT V1 plus C2 e to the AT e to the minus BIT V2. And I can factor out this e to the AT. So we can get C1 e to the BIT V1 plus C2 e to the minus BIT V2. Okay. So basically, I'm going to have oscillations. And this is going to look like cosine of BT and sine of BT. So my period of oscillations is going to satisfy B times T equals 2 pi, just like before. In terms of stability, 3 things can happen. One thing is that A is negative, which means I'm going to have decay. I could have A equal to 0. This means I'm just going to have constant oscillations that neither grow or decay. This is basically 1, and I'm just left with sines and cosines. Or if A is greater than 0, then this thing is going to grow exponentially. Okay. Now, in terms of our vocabulary, how do we describe this? So if we have lambda 1 and lambda 2, case 1 is that they're real and at least one positive. What we say is, sorry, I just want to make sure I get this right, is, okay, we're just going to call this exponential growth. In your book, your authors make the distinction between one being negative and one being positive. They call that a saddle situation. We can just call it growth. But just be aware, some people make a distinction between those things, and they say saddle if one of these things is negative and the other thing is positive. And if they're both positive, we're just going to say they grow, or some people will call it a source. Case 2 is real and both negative. In this case, it's stable or decays. And some people will call this a sink because it basically all your solutions end up dropping down into 0. And then if we have complex roots, the situation is there's 3 things that could happen. Is the real part is negative, right? We're going to decay, and because there's oscillations, well, a lot of sources or a lot of books will say your solutions spiral down into the origin or go to 0. The real part is 0. There's no decay, no growth. And some books will refer to these as just circles or ellipses. Your solutions will move in big ellipses or circles. And then finally, if the real part is greater than 0, it's going to decay. And some books will say your solutions spiral out away from the origin. So it's vital that you be able to look at the eigenvalues, and before you start plotting solutions, recognize, or even before you start calculating eigenvectors, you should immediately be able to discuss the stability and the general behavior of your solutions.